This is video 4.2. It deals with the uses of magnets or magnetism. Now the two central boxes here are really key to try and really get your head around this subject. So current, a flow of electrons, creates a magnetic field. Really key idea. Whenever we have flowing electrons, moving electrons, they create a magnetic field. The other box tells us that a changing magnetic field will create a current if it's near enough to a wire that's holding a current or holding electrons. So key ideas: current turns or creates magnetic fields, changing magnetic fields can create currents in the right circumstances. So we get a number of offshoots from this. So if we have a permanent magnet and then we have a magnet in a wire or around a wire, and they will repel and they'll create a force. So that's hugely useful. Fleming's left-hand rule tells us the direction of the force, and we can make things such as motors from this, which are hugely useful. A speaker essentially also creates motion, but it's a backwards and forwards motion, and a solenoid is just a way of focusing that force in essence. So down here we're back to the opposite. We're creating our currents. So microphones create currents. The air moves it up and down, creating the current. Transformers actually start with a current, but they create a current in their second part. And then we've got generators, two kinds of generators, alternators and dynamos, the difference being alternator creates AC, dynamo creates DC. But to emphasize again, these are the two key ideas. Currents create magnetic fields, changing magnetic fields create currents. So here we are then. There's a slight annoyance right off the bat in that people guessed incorrectly about the direction of flow of current to begin with. So in this example I've got electrons flowing downwards, but something called conventional current goes the opposite way. It's the effective flow of a positive charge. So it's a bit annoying, but we just have to get used to it. So as we said, when we have a current, we have a magnetic field around it. So these lines here represent that magnetic field. The right-hand grip rule tells us the direction of that field. So the thumb points in the direction of conventional current, and our fingers point in the direction of the field. So over here we've got a wire with no current at all, and there is no field around it. So electrons don't create a magnetic field just by sitting around. They have to be moving. So the stronger the current, the stronger the magnetic fields, and then we can see that by the density of the field lines. So here we have the solenoid. Solenoid is basically a coil. So the magnetic field around an individual wire is quite weak. So we put them together, we put them closely together and get this densely packed, more densely packed than you can see here. But together they create a significant magnetic field, sometimes called an electromagnet, but it behaves exactly as though it were a bar magnet. So here we have the repulsion that we mentioned at the beginning. We've got a permanent magnet here. In this case, it's the permanent magnet that is going to be moving away, but it could just as easily be the wire. So we get an interaction between these two magnetic fields as soon as the coil is switched on. So it creates a kick, or a kicking magnet or kicking wire, whatever we want to call it, or however we engineer it. But the essence is we've got two fields and they are repelling. It doesn't matter where those fields came from. So here we have Fleming's left-hand rule. This allows us to predict the direction of this force, and if it's allowed to swing, it becomes a movement. So there are three things here. Each of them have direction. So the first one is the field, magnetic field, from north to south. We have conventional current. So remember, that's the opposite of electrons. So the electrons are moving left to right here, but the current is moving the opposite direction. And we've got, so the current is moving from left to right, and the electrons are moving from right to left. I may have said that wrong, but you get the idea. And force is upwards in this case. So although it's being animated here, we could have predicted that just with knowing the current and the field. So there is a formula that links these four things together: the force, strength of the field, B is its symbol, the current and the length. So it makes sense, longer wire, more exposure, more force, more current, we've already said, has a stronger field, so there's going to be stronger interaction, and if the magnetic field is stronger, our force will also be greater. So the engineering is changed, but the idea is the same. Here we have a motor. So over here, this is a real motor with various coils and so on, but the rotation is essentially the same. There's this repulsion. So here we've got another way of showing this. We've got our field, and then we've got our field around our wire. So as you can see here, that it's like a dart going into the wire, and that gives rise to a force. And providing we keep switching the direction of the current round at strategic moments, so here at the bottom and here at the top, the force will be continuous, and we get our rotation, and our motor works for us. So now we move on to the other side of it, to induce a current, so to indirectly create a current as opposed to having a cell, which is a direct chemical effect. Here we've got a changing magnetic field. In this case it's a bar magnet that's moving, but it could be rotating, or the coil could, any relative motion, and that causes the electrons to move. Now incidentally, it also, because we know that currents create magnetic fields, will create a magnetic field in response to this movement of a magnetic field, and that will always oppose the motion that created it, otherwise you'd be creating energy. But the key thing is we are creating electricity, so a changing magnetic field is creating electricity for us, which is hugely useful. So we can see the same thing here, again, slightly different context, but it's the same bit of physics. So here we've got a wind turbine, it's spinning, and in there there'll be a magnet, and there'll be wires, and we get this changing magnetic field, however we achieve it, and that will create our current in here. So over here, field strength, so a more powerful magnet, more lines being cut, more flux lines being cut. Faster rotation obviously means more lines being cut, more coils means the same. And the more we get this cutting, and it's not literal cutting, but cutting across, the greater the voltage that will be induced. And here we see it on a large scale. This is obviously not a wind farm, but it's going to be steam or something, or water driving these turbines there. So moving on then to the transformer. So a transformer uses both these effects really, and if we follow through what's happening here, we've got a coil here, the primary coil, and we've got the secondary coil here, and as you can see there are more turns here. Now the color here is, I'm using the color of the electrons. They don't really have color, but just to get us the idea, the voltage here is low and the voltage here is higher, and the reason it's higher is because there's more turns. So we have an alternating current going in here. It has to be alternating because it needs to be creating a changing magnetic field. DC won't do that. So we get field lines being cut, and that's, you can see that happening now as these field lines cut this wire. A voltage is induced in the secondary coil, and we get this secondary alternating current, and it'll be of a higher voltage, which is very useful to us. We could have fewer wires, and then we'd have a step-down transformer. So this is the same thing, just shown in algebraic form or formula. So what we're saying here is greater voltage results from a greater number of turns. That's really what this formula is saying. So when we get a question like this, generally I'm a big fan of following the steps, as you know, but in this case I would condense it to this form. So we have some number times a fraction, and depending on whether it's a step up, if it's a step up transformer, it's going to be a vulgar fraction, so a higher number of turns here, lower number of turns here, as it is in this case, and if it's a step down transformer, it will be reversed. So all you need to decide, so if you're after a voltage, this is always going to have a voltage here. All you need to decide is this step up or step down, and that will tell me how I put my number of turns, whether I put the 60 on top or the 20 on top. Lastly then, we've got two devices which we mentioned earlier. We've got a microphone, so as speech or sound, it moves this cone up and down. That induces voltage here in the wires here, because there's a magnetic field around it. That can then be transmitted to a loudspeaker, which is the same thing but in reverse. So here we've got the current that's the starting point. That creates repulsion with the permanent magnetic field. It will move this cone and it will move the air particles.